All right, the Frenchman de Moivres theorem. Here we go. It's actually something we already know, if you think about it. Cos theta plus I sine theta to the power of n is cos n theta plus I sine n theta. And if you think about it, we know that already, because we said the argument of a complex number to the power of n was n times the argument of z. So it's basically the same thing. Now, interestingly, de Moivres originally was just for all integers, but it does turn out it works for fractions as well. So that's not a problem. It does work for fractional powers. Now, to make it a little bit more useful, we put a modulus out the front. So all we're doing is really multiplying by r to the power of n. So there's no drama multiplying both sides by r to the power of n. That's all we've really done. So it's still going to be true. So 1 minus I to the power of 5, yep, could expand the whole thing out, or we could have some fun. Modulus is root 2, argument minus pi on 4. So it's going to be root 2 to the power of 5, cis minus pi on 4, to the power, not to the power of 5, we multiply the argument, so we end up with minus 5 pi on 4 for the argument, and root 2 to the power of 5 for the modulus. We don't leave it as minus 5 pi on 4. If we're writing the answer in mod arg form, because remember in mod arg form we always give our answers between pi and minus pi. But if we are just going to calculate it back into Cartesian coordinates, well, I can leave it as minus 5 pi on 4. Because I'm going to find the cosine of it anyway, so it doesn't matter whether I convert it to in between pi and minus pi. So if we left it in mod arg form, well then I'd write it as 3 pi on 4 instead of minus 5 pi on 4. Root 2 to the power of 5 is 4 root 2. Of course, if we wanted to work it out in its Cartesian, as I say, we could say, oh, well, what's the cos of 3 pi on 4 and sine of 3 pi on 4 minus 1 on root 2 plus root 1 on root 2i, and so there is minus 4 plus 4i. Is that quicker than just expanding out 1 minus I to the power of 5? I mean, if you know your binomial theorem, it's not too hard to expand that out, because it's only 5 terms. But obviously, the higher the power, the more efficient this theorem works for expanding out. But of course, that's not the only thing we use it for. Finding the roots is where it's really useful. So z to the power of n is some complex number. We want to know what z is. So z to the power of n is r cis theta. So z will be the nth root of r, but then the argument we would be dividing by n. Because it's like saying to the power of 1 on n. So multiply by 1 on n, same as dividing by n. But so we can create all the solutions, I go around the circle. So the argument is theta, but I add multiples of 2 pi to say, oh, well, I could go around the circle. I'm in that spot again. I could go around the circle. I'm in that spot again. However many times I need to go around the circle. And then we divide it by whatever that root is that we're finding. Then we sub in 0, 1 up to n minus 1. However, if you know the answers are going to be in conjugate pairs, rather than going 0, 1, 2 and so on, sub in plus or minus 1, plus or minus 2, because that'll create your conjugate straight away by doing plus or minus. Remember, oh, but don't forget the 0, because you need to have consecutive numbers. Let's find the square root of 4i. We've already seen a couple of methods. Let's use this method for finding the square root. So z squared is 4 cis pi on 2. So my answer will be 2 cis 2 pi k plus pi on 2 over 2. I only need 2 solutions, so I'll sub in 0 and 1. Sub in 0, I get 2 cis pi on 4. Sub in 1, I get 2 cis 5 pi on 4. And if we want to actually calculate out the Cartesian, we end up with, there we go, root 2 plus root 2i and minus root 2 minus root 2i. The thing about the roots is they're symmetric. Because we're going around the circle, 2 pi, 2 pi, 2 pi, they're always evenly spaced. So once you know the first solution, you know all the solutions. Okay? Once I knew this answer was pi on 4, I knew I'm finding 2, so that it's got to be symmetric around the circle. The next one's 5 pi on 4. Even when I knew the answer was root 2 plus root 2i, I could place that on the Argand diagram and say, well, it's got to be symmetric. So the other one will be over here, minus root 2, minus root 2i. So there's always symmetry about these roots. Okay, let's find out a fourth root. The fourth root of 16 is?
2.
Oh, yeah. Good work. But that's only one answer.
Minus
But that's only two answers.
C.
Right. Because now, when we're dealing with complex numbers, there's always the same number of solutions as the power. X to the 4 is 16. Or 16 cis 0, we could think of it. So I'm going to say 2 cis, well, 0, didn't write it down, plus 2 pi k over 4. This time I went 0, 1, 2, 3, but I could have gone 0 plus or minus 1, 2 for this one, because they are all real numbers we're dealing with here. So 2 cis 0, 2 cis pi on 2, 2 cis pi, 2 cis 3 pi on 2, 2i minus 2 minus 2i. But again, once I knew the first answer was 2, the others, if I was to draw it, there's 2, they're evenly placed, so they must go every 90 degrees. So I'm going to go there at 90, 180, 270. Must be the third solution. And actually forms a square if I was to join them up. Ooh, fancy. Okay, so that's our introduction into de Moivres theorem.